Jill, have you got the message that recording is started or something like that?
Yes, ma'am, I got.
Okay, fine. You may start. I hope from computer, EC, IT, all the students are present.
Yes, ma'am.
In some of the divisions, Jignesh
Yes,
sir
ma'am.
has taken up this particular topic. So it would be revision for them. And for the students, those who have not come across the topics, for them it would be new. And let us understand this from Jill. Okay, fine. Jill, continue.
Yes, ma'am. So today I'm going to learn the introduction and the absorption and emission phenomena. To understand emission and absorption, first we have to learn some basic things. That is electron hole generation and electron hole recombination. So electron hole generation is when electron hole pair, whenever we are supplying any external energy, the covalent bond will break out and electron and hole pair will generate. And electron hole recombination is whenever electron is in conduction band and it loses its energy. So due to that it came to valence band and again recombine with holes. So that is electron hole recombination, and in this process thermal energy is released. Now according to Einstein, whenever any matter interacts, two absorption and two emission and one absorption will take place. So three process will take place. So from that first we are learning induced absorption. So in induced absorption, first the atom is at lower energy state, and we have to when we are supplying photon radiation, it will interact with this atom, and by gaining energy, by absorbing the energy, it will go to the higher energy state. So it is shown here in the figure that the atom is in lower energy state and we are interacting photon and giving energy to this atom, and the atom is absorbing that energy and it is going to the higher energy state. So before absorption the atom is at lower energy state, and after absorption by gaining the energy it is at the higher energy state. So the rate of induced absorption we are denoting with R12 is directly proportional to radiation rho and population of lower energy level. Means the number of the atom present in lower energy level, that is N1. So R12 that is directly proportional to the number of atom in lower energy level, that is N1, and radiation, that is rho. And by we are here adding one constant, that is B12, which is probability of absorption per unit time. So here we are cancelling the proportionality and we are adding one constant, that is B12. Ma'am, is it okay?
Yes, perfectly okay, Jill. Yes. And how do you say that it is R12? R12 is denoted as you told it is for absorption, induced absorption. But can you identify what is why is that written as 12 R12?
Because the atom is going from lower energy state to higher energy state.
Perfectly okay. Yes, perfectly okay. And you have somewhere told that electron, but immediately you have mentioned that atom. So that is very true. Fine. This is not electronic transition. That is atomic level transition. Fine, Jill. So
Yes,
you
ma'am.
have corrected your mistake. I really like that. Fine. Continue, Jill.
Yes, ma'am. Now next is spontaneous emission. In spontaneous emission, the atom is at higher energy state, and what actually happen here is the atom is at higher energy state, and we are not giving any external energy here. The atom will lose its energy from higher level, and it is falling down by itself to the lower energy state. So here it is shown that the atom is present at higher energy state, and by losing the energy it is coming to the lower energy state, and due to coming from higher energy state to lower energy state, it is emitting some photon, some energy in the form of photon. So electron can come at lower energy state. So here the energy difference, that is of higher energy state and lower energy state, from where atom came, is h mu, which we can denote as E2 minus E1. E2 is the energy of higher energy state where atom is present before the emission, and E1 is the lower energy state after emission. So here the rate of spontaneous emission, that is R21. R21 denotes that 2 stands for higher energy state, means the atom is coming from higher energy state to lower energy state, and here SP denotes the spontaneous emission, which is proportional to population of higher energy state, that is N2. N1 is the population, means the number of atom in a lower energy state, and here N1 is the number of atom in higher energy state. So R12 spontaneous is directly proportional to N2, the population of atom in higher energy level, and by giving out the proportionality sign, we are adding here one constant, that is A12. A12 here is the probability of spontaneous emission per unit time.
Jill, good one. May I add something in that?
Yes, ma'am.
Fine. Uh, uh, are you all listening to me, students?
Yes, ma'am.
Yes, ma'am.
Fine.
Yes, ma'am.
See, over here we have to understand the tendency of a nature. We have to understand the tendency of nature. Nature always believes in equilibrium, or in other words, we can say nature always believes in balance. Whenever there is an instability, or is there any difference between two systems, when systems, they always try to set their equilibrium position. So you just think of that even energy levels are moving to E2 energy level by absorbing certain amount of energy, that is in form of photon, rightly she said. So by gaining some amount of energy, they would be staying at higher energy level. Do you think, friends, they would stay forever there at E2 energy level? Do you think that they will all stay at E2 energy level forever? No. No. The tendency of those atoms to stay more at ground state. You just underline my word. I'm telling that each and every body present on the earth, the all things in nature wants to stay at ground state, wants to spend more time in equilibrium. I hope you get my point. And we people, particularly I'm knowing about Gujarat, that always when we meet somebody, we always ask, Kem cho? I hope you understand my point. Kem cho means if somebody says majama, that means they are at steady state, they are at ground state. What my point?
Yes, ma'am.
Okay. And excitement can be of two types. Positive means you are gaining something and you are excited because of that. And the other kind of excitement means you are in sorrow, you are in some deep sadness. That is also kind of excitement. Understood? So the thing is, everyone believes in nature. In nature, everything believes in balance. Everybody wants to stay or spend more time at ground level. So anyhow, they will they will come back by some emission in form of H nu. They will fall down to E1. And that is what Jill has explained us. I hope you understand, everyone.
Yes, ma'am. Yes, ma'am.
And you know what is the lifetime of atom to stay at E2 energy level? Approximate lifetime खबर छे कोई?
10 raised to minus 9 second.
Perfect. Nanosecond. 1 nanosecond approximate lifetime for an atoms to stay at E2 level. Then in that 1 nanosecond, they are sure to come down. Understood?
Yes, ma'am.
Okay. Yes, Jill, continue. Good one. And
Yes,
A to
ma'am.
one, A to one you have told, right? Einstein coefficient. Einstein was the one who has given us thought of this kind of laser. He has tried with Masser, and he was the one who has given input for lacing action. Fine. So A to one, 2 to 1 it is falling back, 2 to 1 giving rise to some emission. That is why it is known as spontaneous emission. This particular emission doesn't require any external energy. Spontaneous, inherently. Any જાતે જ કરે છે. No stimulation is required. This is the tendency of an atom to fall down by emitting certain amount of photon of particular frequency nu. બરાબર? That is called spontaneous emission. જાતે કરવું, that is spontaneous. Force થી કરાવવું, that is stimulation. In our group also, there are some spontaneous students and there are some stimulated students. Spontaneous students does mean they read or they write or whatever things related to academics they do by themselves. They need not to require a presence of a parent or a teacher or somebody else. Okay, so that is spontaneous. Understood, everybody?
Yes, ma'am.
Fine. Yes, Jill.
Yes, ma'am.
Continue, Jill.
Yes, ma'am. Next is stimulated emission. In stimulated emission, we have to give some external energy to make the atom to come to the lower energy state. So here the atom is present at higher energy state and we have to give some external energy in the form of H mu, photon. So we are interacting one photon at higher energy state and it is falling down to the lower energy state. But here what happened is the photon which we are interacting is also emitting, and H mu energy that is difference is there between higher energy state and lower energy state is also emitting. So here the name is stimulated emission because we have to give some external energy. In spontaneous emission, it is going by itself. So here the energy difference is E2 minus E1, which we have incident on atom, and it emits in the form of photon. Now the rate of spontaneous emission R21 is proportional to the population of higher energy level, that is N2 number of atom in higher energy level. So R21 stimulated is directly proportional to N2 rho. Now by keeping a proportionality constant B21, here B21 stands for probability of stimulated emission per unit time. Now there is one relation which is given by Einstein that is known as Einstein's coefficient. Einstein suggested that whenever there is thermal equilibrium, the upward transition and lower transition both are equal per unit volume and per second. So according to him, the rate of absorption is equal to the rate of emission. Now earlier we have seen that rate of absorption is B12 N1 rho. which is seen here, B1 to N1 row, and rate of emission are both spontaneous and stimulated. So, spontaneous emission is A21N2 plus stimulated emission is B21N2 row. So, by comparing both absorption and emission, we are getting this equation 1. Now, here B21 and 2 row we are keeping on left hand side, and we have to take out common row. So after take outing common row, by subjecting row is equal to A21 N2 upon B12 N1 minus B21 N2. Now after dividing by N2, N1, the row will become A21 upon B12 N1 upon N2 minus B21. Here we have to divide by N21. Here we have to divide it by N2. So we are getting this equation. Now here what is N1? N1 is the number of atom in ground state, means the lower energy state, and the N2 is the number of atom in excited state. So now as per the Boltzmann distribution law, the value of N1 is N0 e raised to minus E1 upon kBt, and N2 is N0 e raised to minus E2 kBt. So now N0 is the total number of atoms, and Kb is the Boltzmann constant, whose value is 1.38 into 10 to the power 23 joule per Kelvin. Now by taking out the ratio N2 upon N1, because we have to use this ratio in this equation. So now taking out the ratio of N2 upon N1, we are getting N2 upon N1 is equals to e raised to minus E2 minus E1 upon kBt. Now we have to substitute this N1 upon N2. We have reciprocal this N2 upon N1. So we are getting positive power of E, that is e raised to h mu upon kBt. Here E2 minus E1 is the energy which is emitting in the form of photon. So that is h mu. So we can also keep E2 minus E1 as h mu, which is shown in equation 5. Now we have to substitute this value in equation 3, which we have seen earlier, this row equation, in which we have to substitute the value of N1 upon N2. So now substituting the value, common, we have to take out the common A21 upon B21 and 1 upon B12 upon B21 e raised to h mu upon kBt minus 1. We have take out common B21 from the denominator. Now according to Planck's theory of radiation, rho is also equal to 8 pi h v cube upon c cube 1 upon e raised to h mu upon kBt minus 1. So by comparing this both the equation, we can see that here A21 and B21, which we have seen in earlier slide, A21 upon B21 is equal to 8 pi h v cube upon c cube, and here with E there is B12 upon B21, so that is equal to 1 here. So B12 is equal to B21 and A21 upon B21 is equal to 8 pi h v cube upon c cube. So now here A21 is the probability of absorption and B21 is the probability of emission. So here we can see that from equation 8 that A21 upon B21 is directly proportional to V cube, because here 8 pi h and c are constant values. So it only depend on V cube. So here pi h and c are constant. So the ratio of absorption upon emission upon absorption is directly proportional to V cube. Now, second point is the ratio of spontaneous emission and stimulated emission. So the equation of stimulated emission is R21 stimulation is equal to B21 N2 rho, and of spontaneous emission is R21 spontaneous A21 N2. Now taking out the ratio of stimulated upon spontaneous, we are getting B21 N2 rho upon A21 N2. Now here we have to divide it by N2. So here we get this equation R21 spontaneous upon R21 stimulated upon R21 spontaneous is equal to B21 rho upon A21, because here N2 N2 got cancelled out. Now from a previous derivation we know that B21 rho upon A21 is equal to 1 upon B12 upon B21 e raised to h mu upon kbt minus 1. We multiply this B21 with rho and dividing it by A21, we are getting this equation. So now comparing this both the equation, because this both the terms are equal, so by comparing this both the equation, A21 stimulation emission upon A21 spontaneous is equal to 1 upon e raised to h mu upon kbt minus 1. So if we reciprocal it, so R21 spontaneous upon R21 stimulated is equal to e raised to h mu upon kbt minus 1. So from this equation we can see that spontaneous emission is much more than stimulated emission, as spontaneous emission is multiplied with R21 stimulation and have some value in the bracket. So the value of spontaneous emission is more than stimulated emission. So here the laser action is not possible. So to make the laser action, we have to make the N2 is greater than N1. Means we have to make the population of atom at high excited state more than the ground state, which is known as population inversion. We have to make the more population of N2 than N1. Ma'am, is it okay?
Yes, Jill. Perfectly okay. I didn't want to disturb you in the derivation, so I've said nothing in between, but very well explained. Students, I hope you are all getting how is the derivation, how the operations to be followed. Everybody understood?
Yes, ma'am.
Yes, ma'am.
Actually, this derivation is all about the ratio of spontaneous emission to stimulated emission. Is it fine? I'll explain it later
Yes,
on. After completion of Jill's presentation, I'll explain some of the 2 to 3 topics. Okay, Jill? Is there anything more
Yes,
in your presentation, Jill?
yes, ma'am. There is one topic left.
There is one topic left. Okay, fine. Let us have your topic completion first, and then I'll be moving for some 2 to 3 topics as I've said. Yes, continue, Jill.
Yes, ma'am. So next we are learning semiconductor laser. So in semiconductor laser, there is a PN junction which is in forward bias, and the electrons are present in N region and holes are present in P region, and they will recombine with each other. Now during recombination, the energy released is in the form of photon, and there is a emitted photon which recombine electron and holes. So this semiconductor laser will work on electroluminance, and there are two ways to fabricate this semiconductor laser. One is homogeneous and second is heterogeneous. So homogeneous is the same material and same band gap are there, and in heterogeneous different material are used and different band gaps are there. And this semiconductor laser is also known as laser diode or injected laser diode. So to make this PN junction for semiconductor laser, we can use the material gallium arsenic, so P type and N type, as germanium and tellurium respectively. So the working is, here what happen, the electron are there in N type and holes are there in P type, and it is in a forward bias. So there is a recombination of hole and electron from N to P, and which results in the emission of photon. The spontaneous emission of photon and external field is there, by which the rate of recombination of electron and hole get increases, because there is some external field because of which the electron and hole recombination is more, and due to that the rate of recombination increases. Now to achieve this, different wavelength are used for donor and acceptor concentration. So here one example is there for band gap is gallium arsenic, whose band gap is 1.44 eV. So Eg, we know that Eg is equal to h mu, and by substituting mu as c upon lambda, we are getting Eg as hc by lambda. So by if we want to find the lambda, then we have to subject hc upon Eg, and h is the constant, c is also the constant, and Eg for gallium arsenic is 1.44 eV. So by substituting this all the value, we can find the wavelength of gallium arsenic as 8628 angstrom. And this is the construction which is shown, the recombination of hole and electron from N to P in forward bias condition, and there is hole in valence band and the electron in conduction band, and by giving the external field, the photon is emitted in the form of light. Now there is some advantage, disadvantage and application of this semiconductor laser. So advantage is modulation of output is possible by controlling the junction current. We have to control the junction current, and we can modulate the output by ourselves. And the semiconductor laser is small, compact, and have high efficiency. The fabrication is also very simple, and output we are getting is continuous, and it will conserve a very low power, and the cost of the semiconductor laser is much more less than any of the laser. And its disadvantage is output is in the form of wide beam, and in simple laser we are getting as a narrow beam. So one disadvantage is this, and threshold current density is large, monochromaticity and coherence is poor as compared to laser, temperature affects output of laser. Application is they are used in long communication, used for optical communication in PC phone, mobile phones, and in laser printer, laser microscopes, and in line lasers. Ma'am, it is done.
Very well explained, Jill. Very well explained. And
Thank you.
yes, in this topic, the basic idea is why have we chosen gallium arsenide material? Students, are you all with me?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Okay, in
Yes, ma'am.
semiconductor we understood N type, P type individually, then we have form a junction, and over here you have seen that how it is useful to get lesser beam output. Okay, can anyone tell me the EG she has shown here, gallium arsenide, through gallium arsenide, which particular color light in laser we will get? Can anyone tell me? Which color would come out as a laser beam light? She has mentioned it wavelength. So that much wavelength is corresponding to which color? I hope you are all busy with Google. ચલો કોને ગૂગલ ઝડપથી જવાબ આપે છે? Who will give me the fast answer? એનું ગૂગલ સારું કામ કરે છે. I'm waiting. This wavelength corresponds to which color? Do you remember yellow color wavelength? Yellow color wavelength ખબર છે બધાને? Yellow color wavelength. I hope students I'm audible to you all. Am I?
Yes.
Yes, I'm waiting for your reply. This wavelength corresponding to
Red
which
line.
color? Huh? Which color? Somebody was telling me.
Red. Blue.
લે એક રેડ અને બ્લુ એક બંને એકબીજા એક એક્સ્ટ્રીમ છેડે આવી ગયા. એક રેડ કે છે ને એક બ્લુ કે છે.
Sorry, ma'am. Red.
Red.
ગૂગલે ખોટો જવાબ ના આપ્યો હોય, જોજો.
Ma'am, wavelength તો વધારે red ની હોય એટલે.
Red.
સારું, which one is the mid light? Mid wavelength કઈ છે and which corresponds
Yellow.
to yellow?
Smallest blue.
એક એક્સ્ટ્રીમ બ્લુ એક એક્સ્ટ્રીમ રેડ અને વચ્ચે યલો. હા કે ના?
હા ma'am.
એટલે ધ્યાન કરતી વખતે ઓમ લખેલો હોય ને, ઓમ છે યલો કલર નો હોય, which enhances our sharpness of mind. યલો કલર છે મીડ છે. I hope you get my point.
Yes, ma'am.
Right? કોઈ મંદિરમાં કે એનું જે પ્રીમાઇસીસ હોય એ યલો શેડ્સ પર વધારે જતું હોય. The reason is this, scientific reason. The mid light, it is
golden ને yellow ગણી શકાય.
ગણી શકાય. એમાં બ્રાઇટનેસ ની ઇફેક્ટ હોય એટલે એ ગોલ્ડન કહીશ. Understood?
Yes, ma'am.
Right. So very nice, Jill. I would like to thank to you. બહુ ટાઈમથી તમે આ બનાવેલું હતું, but we could not find time so that you can present it. Finally, the day has come and you have done it. Good one, Jill. Fine. Very well done.
Thank you, ma'am.
Yes, થોડું એક કે બે નાનું છે point. મારે I just want to add on. You have not missed any of the things, but I just want to add on one or two things. Let us see that. Fine. Anybody has any question for Jill? Anybody wants to ask Jill regarding the topic which she has explained? Want to ask any single question? Okay, fine. Jill, I hope you everybody understand everything. Thank you very much, Jill.
Thank you, ma'am. Ma'am, can I stop presentation?
Let me find clappings. Digital clapping આવે ને હું શોધું છું. Students તમને મળે તો even you can clap for her. I'll clap it over here physically. Fine, Jill. Thank you so much. Yes, you can keep it down. You can keep it down.
Yes, ma'am.